the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a final video on diagonalization of symmetric matrices for linear algebra students. We're going to talk here in this video about the spectral theorem and decomposition, or spectral decomposition, that is. So let's go ahead and get into it. What is the spectral theorem? Well, to get into that, we need to know what the spectrum of a matrix is. The set of eigenvalues for a matrix is simply called the spectrum. So when you're handed a matrix, and let's say it has eigenvalues 1, 2, and 10 has multiplicity 5 or something like that, then the spectrum of the matrix is 1, 2, 10. That's a set of the eigenvalues. Of course, 10 had multiplicity 5, so you could technically list that out 5 times if you wanted to. You don't have to, but you could. And the idea of having something, a name to apply to the set of eigenvalues, really allows us to have a bigger conversation about the eigenvalues, the set of eigenvalues for a matrix. So this theorem is called the spectral theorem for symmetric matrices, meaning there might be another spectral theorem, right? If this one says for symmetric matrices, who knows? Well, given a square symmetric matrix, which by the way, all symmetric matrices are square, then you know that matrix must have the following properties. I'm not saying that these properties are equivalent. This is not an equivalence theorem or an equivalence statement. This is literally if your matrix is symmetric, these things are true, period. So if you have a symmetric matrix, well, it has n real eigenvalues counting multiplicities, as long as it's an n by n matrix. So in my example where I said 1, 2, and 10 were eigenvalues, where 10 was an eigenvalue with multiplicity 5, A would be considered to have 7 eigenvalues, because it has 1, 2, and then 10 with multiplicity 5 on it. So therefore we have 7 eigenvalues altogether. The dimension of the eigenspace for each eigenvalue must equal its multiplicity as a root of the characteristic equation. That is, the dimension of the eigenspace associated with lambda equals 1 is 1, because it's multiplicity 1. The dimension of the eigenspace associated with lambda equals 2, well, that's also 1. But the dimension of the eigenspace associated with lambda equals 10 would be 5, because the multiplicity of the eigenvalue 10 is 5, for this very fictitious example. Now, this is only true for symmetric matrices. Well, not only true for symmetric matrices, but you know it's true for symmetric matrices. How's that? Another thing, the eigenspaces are mutually orthogonal in the sense that eigenvectors corresponding to different eigenvalues are orthogonal. We saw it in the last example in the last video, that if you have, for example, a 3 by 3 matrix with only 2 eigenvalues, well, the eigenvectors associated with those 2 distinct eigenvalues will be orthogonal if you have a symmetric matrix. However, one of those eigenvalues had multiplicity 2, because you have a 3 by 3 symmetric matrix with only 2 distinct eigenvalues, so one of them had to be multiplicity 2. For that eigenvalue with multiplicity 2, its associated eigenvectors need not be orthogonal. And we saw that again in the last example in the last video. And that created this question of, well, wait a second, I thought you said that when you diagonalize a matrix into P times D times P inverse, that the column vectors in the matrix P must be the eigenvectors of A. But that's actually not true. They can be the eigenvectors of A, but as long as they span the space that is created by those eigenvectors, they need not actually be the eigenvectors. And that's what we used in the last video. We were able to take those 2 eigenvectors associated with a single eigenvalue and create an orthogonal basis for that eigenspace. Or maybe you want to call that an orthogonal eigenbasis. But anyhow, part C here just says eigenspaces are mutually orthogonal in the sense that as long as eigenvectors belong to different eigenvalues, they're going to be orthogonal. And finally, whenever you're handed a symmetric matrix, you know immediately it's orthogonally diagonalizable. You can always force an orthogonal eigenbasis for your eigenspace. Now, most of these are left for the homework problems, usually for students to prove. So I'm not going to prove any of these here. However, I will prove the next theorem that we're going to use prior to our final example for this topic. And that final theorem is called the Spectral Decomposition Theorem because it's very spooky, it's spectral. So suppose you have a matrix A, it's square, n by n, and it's symmetric, with orthonormal eigenvectors, u sub 1 through u sub n, and corresponding eigenvalues lambda sub 1 through lambda sub n. Then that matrix A can be decomposed into this linear combination of matrices right here. It's lambda 1 times, if u sub 1 is the eigenvector associated with lambda 1, it'd be u sub 1 times u sub 1 transpose. That's actually an n by n matrix. And that pattern continues all the way until you get to lambda sub n, and that eigenvalue can be multiplied against its eigenvector, u sub n times u sub n transpose, which again is a matrix. Now remember, these actually have to start as orthonormal eigenvectors. So they do have to be actual eigenvectors. They cannot be orthogonal eigenbases or something like that. They actually have to be eigenvectors. That's distinctly different than what we did in the last video. So I'm going to repeat this again because I want to drive the point home. This decomposition here is only true if you can find orthonormal eigenvectors for A. And that usually can only happen if you have distinct eigenvalues. So let's just dive into the proof and then we'll go into a final example here. Well, since A is symmetric, we know that A must be equal to P times D times P transpose. That is, A can be written as some matrix P, which has actually as its columns the eigenvectors of A. And we were told, by the way, I didn't write it in the proof, but we were told that A has orthonormal eigenvectors. So each of these eigenvectors that are in P are orthonormal to each other. That is, P is an orthogonal matrix. Therefore, when you do the diagonalization of A, which normally is P times D times P inverse, because P is orthogonal as a matrix, P inverse is equal to P transpose. So if A is symmetric and it has orthonormal eigenvectors that should have actually been written right here, then A can be rewritten as P dP transpose. Of course, P, again, is just a matrix containing the column eigenvectors, right? So all the eigenvectors of A, and remember, they're all orthogonal to each other and each has length 1. So they are not only orthogonal, they're orthonormal. D is the matrix containing the associated eigenvalues, and obviously P transpose is just a transpose of P itself. So that'd be U sub 1 transpose as the first row, all the way down to U sub n transpose as the final row. Now what we're going to do is multiply P against D. When you do that, what actually happens is that each column gets multiplied by the respective eigenvalue. This is something you might have already proved early on in this course, but easily have forgotten because it's been a while. However, it is true that when you take a matrix and multiply it by a diagonal matrix, the result will be, well, the matrix of these vectors where the coefficients are the respective entries along the main diagonal of D. And that's what we have right here. And then finally, this matrix product you can write as this guy right here, lambda sub 1 U sub 1 times U sub 1 transpose plus so on and so forth down the line to lambda sub n U sub n U sub n transpose. And that is actually the proof. A is actually equal to this linear combination of matrices right here. It's actually not too terrible. Most textbooks have it kind of written in a sidebar or something like that. So let's go ahead and use the spectral decomposition theorem. We're going to construct a spectral decomposition of the following matrix. That is, we're going to write this matrix as a sum of matrices. And the sum of the matrices is just going to be the sum of these matrices that consist of the orthonormal eigenvectors of A. Now, something that we need to be very clear about here. If we go to find eigenvalues of A here, and we find that we only have 1 or 2, then spectral decomposition is going to be pointless because you do not have orthonormal eigenvectors. It's only possible really if your symmetric matrix has n distinct eigenvalues. Now again, you might say, but wait a second, I remember in the last video, you actually rewrote A and diagonalized A because you were able to find 3 orthonormal eigenvectors. And I'm going to tell you that's actually not true. In the last video, I had this matrix right here, and I found the eigenvectors. It is true, but these eigenvectors were actually not orthogonal to each other. Forcing them to be orthonormal if they were orthogonal is not a big deal, but they're not orthogonal to each other because we only had 2 eigenvalues for this 3x3 symmetric matrix. And so what you are thinking of, if you're thinking, wait a second, he did totally find 3 orthonormal eigenvectors. Nope, I found P, which consisted of 3 orthonormal vectors. It is true, but 2 of them were totally not eigenvectors. Actually, one of them was not an eigenvector. This middle one wasn't an eigenvector, but the 2 edges were actual eigenvectors. This is an eigenvector, that's an eigenvector, because if you look at the original eigenvectors, 1, 1, 1 was an eigenvector, so divide that by root 3, it's still an eigenvector. And negative 1, 1, 0 was an eigenvector, so divide that by root 2, it's still an eigenvector. However, v sub 1, 2 was an eigenvector, and if you notice, this is not a multiple of v sub 1, 2. It's not an eigenvector. And you say, but how the heck did you get away with building P like this? The rules for building P do not require that your columns are eigenvectors. It just requires that your columns span the eigenspaces. And the easiest way to do that normally is with eigenvectors. But we did it by building orthogonal projections instead. Or in other words, we built an orthogonal eigenbasis associated with lambda equals -1 in that case. So again, I just want to remind you, we did not actually find orthonormal eigenvectors in this example. But hopefully we can do that in this example right here. And we get 3 distinct eigenvalues, which is super duper nice because we'll have 3 distinct eigenspaces, which means for the symmetric matrix that we started with way up here, which totally is symmetric, right? It's a mirror image across that main diagonal. That means that matrix is diagonalizable. Specifically orthogonally diagonalizable very easily. Not only that, but by this theorem right here, because we're going to have 3 distinct eigenvalues, all of our eigenvectors are going to be orthogonal to each other, and we can normalize them so they be orthonormal, and then we can decompose A into this little linear combination right here. Now at this point, you've done all the eigenvalue, eigenvector work for so long, I'm just going to quickly write down the corresponding eigenvectors for these eigenvalues. Note that each of these vectors are actually orthogonal to each other. You can double check it, go through if you want to. They really are orthogonal to each other. And I'll go ahead and normalize them. So there we have now 3 orthonormal eigenvectors for the matrix A. For simplicity's sake, I'm actually going to relabel these as just U1, U2, and U3, just because, well, it's a little bit cleaner to do that. And when you do that, by the spectral decomposition theorem, we know that this matrix A, all the way at the top, there we are, can be written as lambda sub 1 times the normalized eigenvector for lambda sub 1 times that normalized vector transpose. And so on and so forth down the line. Now this spectral decomposition that we're doing right here is not super useful yet. However, it is actually very useful when you go to quadratic forms, which is actually the next big topic and final topic in linear algebra. So being able to decompose a symmetric matrix into the sum of these matrices right here can be very, very helpful. If you want to multiply out these vectors, you're more than welcome to. I'm actually not going to. I'm going to escape out of the video for right now, but you could totally do that if you so desire. It's just column matrix times row matrix multiplication. All right, that does it for this video, and I hope it helps you out, and I hope you have a great day. Be a wonderful human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.